Problem number 9 is one that I'm guessing a lot of you guys looked at and kind of just went, huh? And had no idea what it was that we were talking about and probably said, boy, we didn't talk about how to do this at all in class. Well, we kind of did, everybody. There are a couple of ways of explaining this. The more thorough one would probably be for me to tell you that this first expression right here, df du, might be more easily understood if you wrote this right there as f prime, the derivative of f, taken with respect to u, and that this one right here would be what? It would be u prime taken with respect to x is equal to 6, and then we could make a composition function out of these two. But you know what? I don't think anybody cares about understanding it that way. Let's do this nice and quickly. Most calculus students prefer Isaac Newton's methodology of naming functions with f and f prime. But Leibniz's notation in terms of the dy and the dx and the whatnot is actually a lot more useful to us because it actually encourages us to think of the numerator and the denominator right here as two separate quantities. They're called differentials. They basically mean delta y and delta x, but with a limit as that difference is approaching 0. All right, long story short, here's the really fast way to do this problem. We are supposed to come up with the value of df dx, and what we're going to do here, guys, this is normally kind of the opposite of what I want to tell you to do, treat the numerator and the denominator of all these expressions separately. So what's going on right here? We've got the derivative of f taken with respect to u. Now you'll notice, look at the blue statement that I have right here. My numerators are the same, df and df. That makes sense, but my denominators are not, dx and du. But what do they give us over here? The derivative of u taken with respect to x. And if I were to just multiply df du by du dx, if we do what we don't normally do, which is to treat both the numerator and the denominator of a derivative expression as its own separate side within a fraction, then the du on the bottom right here cancels out with the du on the top right here, leaving us with df over dx, which is exactly what we're looking for. So you can do this with derivatives if they're written in Leibniz's notation. So what does that do for us? The value of df du is 2. And if we multiply that by, here we go, the value of du dx is 6. We've just answered our question, guys. The value of df dx, the derivative of f taken with respect to x, is the product of 2 and 6, and our answer there is 12.